Assalamualaikum and hi everyone. This is the second part of chapter 4.4. Today we're going to continue with our discussion on the method of undetermined coefficients. This method is used to find the particular solution for the non-homogeneous linear differential equation with constant coefficients. And the method that we have used is specifically known as the superposition approach. Let us begin by looking back at equation number 18, which is displayed in the first part of chapter 4.4. This equation is of nth order, it is linear in y and the coefficients are all constants, and the gx is not equal to 0. Since the gx is not equal to 0, this equation is identified as a non-homogeneous equation. When we solve equation number 18, when we solve a non-homogeneous linear equation with constant coefficients, we will get the general solution. And the general solution is given by y is equals to yc plus yp. Yc is the complementary function. In other words, it is the general solution for the associated homogeneous equation, whereas yp is the particular solution for the non-homogeneous linear differential equation. I have already explained this table to you in the first part of chapter 4.4. Let me now add some additional information for you to understand better of how to form the trial yp given the function gx. Let us look at example number 2. Suppose the gx is a linear function such as this. Gx is equals to 5x. So how to write down the form of the yp? The yp must follow the form of the gx. If this is linear, this is an equal function of degree 1, then the yp must also be of degree 1. So we have here 5x, meaning 5x is the same as 5x plus 0. So 5x will be replaced by ax, and the plus 0 will be replaced by plus b. In the second example, we see a quadratic function 3x squared minus 2. Notice that the x term in this quadratic function is missing. Why is the x term not listed here? This is because the coefficient of x is 0. So in this case, we have to write down the form of the yp ax squared plus bx plus c. Even though the x term is missing in the function gx, but you have to include the x term in the form of the yp. Example number 4, notice that the x squared term is missing in this cubic function, but to form the trial yp, you must write down all the terms in the cubic function, including the x squared term. So we have ax cubed plus bx squared plus cx plus d. For the sine and cosine function, in order for us to write the form of the yp, you must maintain the type of the argument written for the given sine or cosine functions. In this case, the gx is sine 4x, and therefore you have to write the form of the yp as a sine 4x plus b cos 4x. Suppose this is sine 3x, then you change this into a sine 3x plus b cos 3x. So the argument for the sine function as well as the cosine function must be maintained whenever you want to form the trial yp. For the exponential function, you must maintain the power of the e in order to form the yp. If this is e to the 5x, then the yp also contains the function e to the 5x. Suppose you change the power of e, you write it as e to the power of 2x, then over here we have ae to the power of 2x. In the previous lesson, I have already illustrated to you how to solve two problems on non-homogeneous linear equation with constant coefficients. It seems that finding yp for those two problems are quite straightforward. However, there are other problems where finding the yp is not as easy or not as straightforward as they seem to be. We may have to apply a couple of rules to determine the yp depending on the cases involved for the given problems. So let us understand what the rules are. So rules for determining the yp. Case number 1. The gx may contain a sum of n distinct functions. Okay, so this is the non-homogeneous linear differential equation, ay double prime plus by prime plus cy equals to gx. So the right side, the gx, is actually comprises of a sum of several distinct functions, g1 of x plus g2 of x plus some other terms in between plus gn of x. So if this is the case, then how do we find the yp? So for case number 1, the rule number 1 is this. Yp will be the sum of yp1 plus yp2 plus some other terms in between plus ypn. So the yp1 is the particular solution corresponding to the first function g1. The yp2 will be the particular solution corresponding to the function g2. And the ypn will be the particular solution corresponding to the function gn. So this is case number 1, rule number 1. Case number 2. If there is a term in the trial yp that duplicates a term in the yc, then what should we do to find the yp? That yp must be multiplied by x to the n, where n is the smallest positive integer that eliminates the duplication. So what it means is this, you have to check whether there's any duplication of the trial yp with the yc, and if there is a duplication, you need to multiply that yp by x to the power 1. Suppose after you have multiplied by x to the power 1, you can see that there's still duplication between the yp and the yc, then you have to continue and multiply that yp by x to the power 2, and so on. So you have to keep on multiplying by x to the n, where n is the smallest positive integer that eliminates the duplication. Okay, this is an example of a problem. Find the general solution of y triple prime plus 2y double prime equals to x plus 2 minus 8e to the minus 2x. Of course, the first part is to find the yc, the complementary function, and finding the yc should not be difficult for you now. You have to start by forming the associated homogeneous equation. In other words, whatever is written on the right side, this is your gx, you must replace it by 0. So the equation now is y triple prime plus 2y double prime equals to 0. So this is a third order homogeneous linear differential equation, and this homogeneous equation is associated to the original non-homogeneous equation. The auxiliary equation is m cubed plus 2m squared equals to 0, and when we factor the m squared, we'll get m squared multiplied by m plus 2 equals to 0. So solving this equation, we get the first two roots equals to 0, because if m squared equals to 0, that means m multiplied by m equals to 0, and therefore the first two roots m1 and m2, they are both equals to 0. And the third root, we get it from this factor, m plus 2 equal to 0, so the third root is equals to negative 2. So we have a case of repeated real roots together with a distinct real root. For the first root, if m1 is equal to 0, therefore y1 will be e to the m1x equals to e to the 0x, which is 1. Since the m2 is repeating m1, so y2 is x multiplied by y1, so x multiplied by 1, which is x. And for y3, since m3 is another real number, so the formula for the solution is e to the m3x. Substitute m3 by negative 2, so we are getting y3, which is e to the power of negative 2x. So now we can form the yc, which is given by c1y1 plus c2y2 plus c3y3. Now remember, this yc is actually the complementary function, or it is the general solution for this associated homogeneous equation. So yc is c1, which is the y1, c1 times y1, so y1 is 1, plus c2y2 plus c3y3. Okay, so this is the yc. Now we're going to find the yp, the particular solution for the non-homogeneous equation. The gx is equals to x plus 2 minus 8e to the negative 2x. Notice that this function gx is made up of two distinct functions. The first function is a linear function, x plus 2. So we name this as g1. And the second function is an exponential function. We call it as G2. So we have here a sum of two distinct functions. So this is case number 1. So what is rule number 1? Rule number 1 is that if you have two distinct functions, G1 and G2, therefore you need to find YP1 and YP2. So YP1 will be the particular solution that corresponds to the function G1, whereas YP2 will be the particular solution that corresponds to the function G2. Okay, so let us look at the function G1. G1 is x plus 2. This is a linear function. Now I'm going to find the trial particular solution YP1. So I write this as my first trial. I want to check whether my first trial can be applied or can be used or not. So this is what I'm going to start with. G1 of x is a linear function. Therefore, YP1 must also be linear. Linear, linear. So you write down ax plus b. Now let us look at case number 2. Case number 2 says that if there is a duplication between the yp and the yc, then you have to multiply the yp by x. Now let's check whether there's a duplication between this yp1 with the yc. When we compare between these two, we notice that there is a similarity between the yp1 and the terms in the yc. Notice that ax plus b duplicates, or in other words, it has a similar form with c1 plus c2x. Okay, the c1 and plus c2x in the yc. Because this ax has a similar form with c2x, and this constant, the b, has a similar form with this constant c1. So their forms are similar. In other words, ax plus b duplicates c1 plus c2x. So since there is a duplication between the yp1 and the yc, then we have to multiply yp1 by x. So that is the rule for case number 1. Okay. Alright. So now we're going to multiply yp1 by x. So we'll get yp1 as ax squared plus bx. Let's check again whether any of these two terms duplicate the terms in the yc. Okay, now we have a constant times x squared. We do not have a constant times x squared in the yc, but we have this term which duplicates the term in the yc. This term bx, okay, bx duplicates the term c2x in the yc. Okay, c2x in the yc. So we have a constant times x in the yp, and in the yc we also have a constant times x. So they are of the same form. Okay, even though the constant here is labeled as b, the constant here is labeled as c2, but still they are considered as having the same form. Okay, so case number 2, rule number 2, if there is a duplication between the term in the yp with the term in the cx, we have to multiply that yp by x again. Okay, so we have to multiply this whole part of yp1 by x again. Even though only this part duplicates, but the rule is that all of this must be multiplied by yp1. Okay, so this is the third trial. We multiply yp1 by x another time, so we get ax cubed plus bx squared. It seems that this term ax cubed does not have any similarity with any term in the yc. Also, this term bx squared does not have similarity with any term in the yc. So these two terms do not duplicate any term in the yc. Okay, therefore we are going to use this yp1 in our work after this. Alright, so we have tried multiplying yp1 by x. For the first time, it doesn't work. We multiply by x another time, it doesn't work again. Then only for the third trial, then it seems that the yp1 has no similarity with the form of the yc. So this yp1 will be accepted as the yp1 in our work after this. The G2 of x is negative 8e to the negative 2x. How do we write down the form of the function yp2? Okay, so let us look at the first trial of yp2. Remember, to form the yp2 must follow the form of the gx. So this is an exponential function, so negative 8 will be replaced by capital C. Now we don't use the letters A and B anymore because the letters A and B has been used in YP1. So now let us use a different letter, call it as a C. So this negative 8 is replaced by capital C multiplied by the exponential function e to the minus 2x. Now we have to check, does this YP2 duplicates the term in the YC? Yes, if you check, notice that c e to the minus 2x has a similarity with a term in the YC, which is c3 e to the minus 2x. Even though this one here we call the coefficient as c, whereas this part here the constant is labeled as c3, but they have similar forms. So since there is a duplication between the YP2 and the term in the YC, therefore we have to multiply YP2 by x. Okay, so this is the second trial for YP2. We multiply YP2 by x. So we get constant x e to the minus 2x. And this term does not duplicate any term in the YC. Okay, so this term, this should be spelled as THIS, sorry. So this term does not duplicate any term in the YC, thus we will use this second trial of YP2 in our work after this. Okay, once there's no more duplication, we shall accept this as the YP2. Alright, so we have taken this as our YP1 and we have taken this as our YP2. So the ones that I ticked will be taken as the particular solution for the corresponding G. So we are going to write down the form of the YP. YP is equals to YP1 plus YP2. Now YP1 is ax cubed plus bx squared. So this is the one that we have selected. Plus, and YP2 is this one here, cx e to the minus 2x. Okay, so this is the correct form of the YP. And after this, the method is as before, where we have to differentiate the YP. How many times do we need to differentiate? Since this dE is of third order, so we have to differentiate it 3 times. Okay, so I've shown you the differentiation of the function YP, YP prime, YP double prime, and YP triple prime. The next step is to substitute YP double prime and YP triple prime into the left-hand side of the non-homogeneous equation. Okay, so this is the YP triple prime plus 2YP double prime is equals to x plus 2 minus 8e to the minus 2x. Okay, YP triple prime is given by 6a plus 12ce to the minus 2x minus 8cx e to the minus 2x plus 2 times YP double prime. So this, all of this in the bracket is the expression for the YP double prime equals to x plus 2 minus 8e to the minus 2x. Now regroup the left side of the equation. So you collect all the terms which are just constants. We have the 6a plus 4b. So these are the terms which are regarded as constants, constant terms. And then we have 12ce to the minus 2x minus 8ce to the minus 2x. That will give us 4ce to the minus 2x. A negative 8cx e to the minus 2x will be cancelled with this 8cx e to the minus 2x. So this term cancel. Plus 12ax. Okay, plus 12ax is equal to the right hand side. X plus 2 minus 8e to the minus 2x. After we have regrouped the left side of the equation, we can now compare coefficients of like terms. So we shall start by comparing the constant terms. On the left side, the constant terms are 6a plus 4b. On the right side, the constant term is the number 2. So 6a plus 4b is equals to 2. So this equation are labeled as equation number 1 because I cannot solve this equation yet. There are 2 unknowns which will need to be found after this. Coefficient of x, this term contains the coefficient of x 12a, and on the right side the coefficient of x is the number 1. Okay, 12a is equals to 1. So solving this equation we'll get a as equals to 1 over 12. Coefficient of e to the minus 2x. Okay, when you look at the left side, there's only one term involving e to the minus 2x. So the coefficient of this e to the minus 2x is 4c. so equals to for c. On the right side, there is a term involving e to the minus 2x, and the coefficient of this is negative 8. So for c is negative 8, therefore c is equals to negative 2. So we have already known a, we have already known c, and we can also find b from equation 1 because a has been known to be 1 over 12. So solving for b, we get b as equals to 3 over 8. Okay, so we already known the values for the a, b, c. Now let's go back to the form of the yp. Yp was given as ax cubed plus bx squared plus cx e to the minus 2x. Now we substitute a by 1 over 12 and b as 3 over 8 and c as negative 2. So this is the form of the particular solution. Lastly, we write down the general solution. Y is equals to yc plus yp, y equal to c1 plus c2x plus c3 e to the minus 2x. So this is the form of the yc plus the particular solution 1 over 12x cubed plus 3 over 8x squared minus 2x e to the minus 2x. Next question, find the form of the particular solution yp for the differential equation. Okay, so this is a 6th order differential equation, and in this equation we are supposed to find the form of the particular solution. In other words, once you have got the particular solution yp, you can accept that as the end of your work. You don't have to solve the equation. You don't have to find the coefficients a, b, c, d, and so on. Okay, as usual, we need to find the yc. Why do we need to find the yc? Because before we find the yp, we have to make sure that the yc has been formed in order for us to check the duplication between the yp and the yc. Okay, so this has to be found first, even though the question is asking you to find the yp. Okay, so find yc. So we have to change the right hand side as 0. So the right hand side has been replaced by 0. The gx on the right side is equals to 0. So we have this equation in the form of 6 derivative of y minus y double prime equals to 0. The auxiliary equation will be m squared minus m squared equal to 0. Factor the m squared. So m squared times m to the 4th minus 1 equals to 0. So m squared is equals to 0, or m to the 4th minus 1 is equals to 0. So if m squared is equal to 0, we get two roots. Both of them are equal to 0. And if m to the 4th minus 1 equal to 0, we can factorize the left side. We get the product of m squared minus 1 and m squared plus 1 equal to 0. If m squared minus 1 is equal to 0, that means m squared is equals to positive 1. Okay, move negative 1 to the other side, and therefore m will be plus or minus square root of 1. So we are getting two real numbers. The m3 is positive 1 and m4 is negative 1. For this factor m squared plus 1, if it is equals to 0, then we shift positive 1 to the other side. So we'll get m squared as equals to plus or minus square root of negative 1. But square root of a negative 1 is identified as I. So in other words, m squared is plus or minus I. So the 5th root is positive I and the 6th root is negative I. So we see we have a combination of repeated real roots, distinct real roots, and complex conjugate roots. Okay, so this is the form of the y1. y1 is 1, okay, because the m1 is equal to 0. y2 is x multiplied by y1. y2 is x. y3 is e to the m3x. Okay, substitute m3 into here, so y3 is e to the power of x. y4 is e to the m4x, substitute m4 as negative 1 into here, so y4 is e to the minus x. M5 and M6 are complex conjugate roots, so we use the formula e to the alpha x cos beta x. Alpha is 0 for these two cases, so e to the 0x, e to the 0x for y5 and y6, and the beta is equals to 1, 1i, negative 1i, so beta is 1, 1 here and 1 here. So e to the 0x cos 1x or cos x, so y5 is just cos x, and y6 will be e to the 0x sin x, or in other words, this is equal to sin x. And now we can form the yc, which is the general solution for the associated homogeneous equation. So yc will be equal to c1 plus c2y1 plus c3y3 plus c4y4 plus c5y5 plus c6y6. Now let us determine the yp. Notice that the gx on the right side is a sum of four distinct functions. The first one is a quadratic function. We call it as a g1. The second one, the g2, is a product of a linear and exponential function. The third one, which is g3, is a product of an exponential function and a sine function, whereas the last one, g4, is a cosine function. So let us determine the yp's for each of these. G1 is 3x squared minus 1. So how do we form the yp1? Okay, so if this is a quadratic, therefore yp1 must also be a quadratic function. So if this is 3x squared minus 1, yp1 will be ax squared plus bx plus c. Now check, is there any term in this yp1 duplicates the term in the yc? Yes, we have these two terms, bx plus c. Bx plus c is similar to c1 plus c2x in the yc. Since there is a duplication between these two, then the rule is we have to multiply yp1 by x. Okay, so we need to multiply yp1 by x. You get ax cubed plus bx squared plus cx. Check one more time. Is there any term in the yp1 that is similar to the term in the yc? After checking, we found out that the cx, this term here, duplicates c2x in the yc. So since this term has a duplication with a term in the yc, the rule is all of these terms in the yp1 must be multiplied by x. Okay, so multiply yp1 by x again. So this is the third trial for yp1. So we multiply ax cubed by x, multiply bx squared by x, multiply cx by x, we'll get ax to the fourth plus bx cubed plus cx squared. So this is the form of the yp1. Once we have multiplied everything by x, we notice that none of these terms duplicate any term in the yc. And therefore we are satisfied that this should be the form of the yp that we are going to take in the final, and we're going to use in the final answer. So I tick this one, that means you're going to take this form of the yp1. G2 is 2x e to the power of x. So how do we write down the yp2 corresponding to the function G2? Notice that this is a linear function multiplied by an exponential function. So the form of the yp2 will be as follows. yp2 is a linear function. Now we have already used up the letters a, b, c. Now we are going to use the letters d and e. Okay, so this is a linear function dx plus e multiplied by e to the power of x. Now let's check whether there's any duplication of these terms in the yp2 with the yc. If you expand this, you get dx e to the power of x plus e times e to the power of x. Notice that the product e times e to the power of x duplicates c3 e to the x in the yc. Okay, these two have a similar form. Since there is a duplication in the yc, so we need to multiply all of these with x. Okay, so dx we multiply by x, e also you multiply by x, so we get yp2 as dx squared plus ex times e to the power of x. So now, after checking, we notice that the product dx squared times e to the power of x does not duplicate any term with the yc. And this product ex e to the power of x also does not duplicate any term in the yc, and therefore we are satisfied that this will be the form of the yp2 that we will use in the final answer. Okay, so I tick this part of the yp2 which we are going to use it afterwards. The ones which I do not tick will not be used in our answer. Okay, G3 is a product of exponential function and a sine function. So how do we write the form of the yp3? Okay, yp3 must follow the form of the function g. Okay, so this constant -1 will be replaced by the constant f, and we follow the product written here, e to the 3x sine x. So f e to the 3x sine x. But remember, the sine x, the function sine always goes together with the function cosine. So you have to add another term involving the cosine function. So what you have to do is to just replace f with another coefficient known as g, and replace the sine by the cosine function. So this will be the complete form of the function for the yp3. And when we compare these two with the terms in the yc, we notice that none of these terms duplicate any term in the yc. Thus, we will use this yp in the final answer. So since there's no duplication, there's no necessity for us to multiply this yp3 by x. Okay, lastly, we look at g4. g4 is equal to 7 cos x. So how do you write down the yp4? yp4 will be as follows. Okay, this number 7 will be replaced by the coefficient h multiplied by cos x. But since cos must go together with a sine function, so the next step is to add another term, I sine x. So we just change the h into I and change the cosine into sine for this second term. Right, so now we have the yp4 given by h cos x plus I sine x. But if you compare these terms with the ones in the yc, you notice that h cos x duplicates c5 cos x in the yc, and I sin x duplicates c6 sin x in the yc. So what to do now? We need to multiply yp4 by x. Okay, so multiply yp4 by x, we get hx cos x plus ix sin x. And it seems now that none of these terms duplicates any term in the yc. And therefore, we will use this second trial of yp4 in the final answer. Okay, so having found all those confirmed yp1, yp2, yp3, yp4, the ones that I've did, we are going to write now the particular solution yp, which is the sum of yp1 plus yp2 plus yp3 plus yp4. So you substitute all these answers into the final form. So yp1 is ax to the fourth plus bx cubed plus cs squared. yp2 is dx squared plus ex multiplied by e to the power of x. yp3 will be fe to the 3x sin x plus ge to the 3x cos x. And yp4 is hx cos x plus ix sin x. Okay, so we have already given the form of the particular solution as required in the question. So the question doesn't ask us to solve the equation. In other words, you don't have to differentiate this 6 times to get the answers for the A, B, C until I. No need to do that. Okay, just write down the form of the particular solution, and that is enough to answer this question. Alright, so that's all for the lesson today, and thank you for your kind attention.